Good evening, all. I'm Manupur Vikramsinghe, and I welcome you to the first session of the series of webinars on submarine fiber optic cables organized by IEEE Communications Society of KDU. Today's session is conducted by Dr. Sumudu on the topic of submarine fiber optic cables. Before we start, I would like to give a small introduction on our speaker, Dr. Sumudu. Dr. Sumudu Edirisinghe obtained a first-class honors degree in electronic system engineering in 1997 and in 2001 was awarded a PhD in optical communication from the University of Essex. Over the next 20 years, he has been working as a research and development engineer and design engineer for several telecommunication equipment manufacturers in Europe and USA. He holds 3 US patents and has several publications in the area of expertise. He is an international consultant in submarine fiber optics cables, and he is a visiting lecturer in optical communication at University of KDU. He also is a postgraduate examiner at University of Moratuwa. He is currently one of the leading experts in upgrading and testing submarine optical cables, traveling to over 50 countries to provide his expert opinion. He is a senior member in IEEE and a member of the Optical Society of America. Sir, we warmly welcome you to this webinar. And a little notice to all the participants. We highly encourage and appreciate questions to be asked so that the slightest clarifications can be addressed. Feel free to type them in the Slido link we have provided in the chat below. Without further ado, I cordially invite Dr. Sumudu to carry on with the webinar. Thank you.
Okay, it's a pleasure to address you all in this topic. My webinar is going to take 3 days. I conducted a similar one for IET a few months back, and it was a single session. I felt it was too much concentrated. So I'm going to divide this into maybe 1 hour 15 sessions, 3 of them. So today my focus is going to be about give you a little bit of an introduction to telecommunication, and I'm pretty sure all of you are already started or have heading down the path of choosing telecommunications as your specialty. How they're manufactured, how they're laid. And then the last week, we will look at the futuristic stuff. By the time when you become graduates and when you try your hand in this industry, what awaits you is what I'm going to talk to you at the end of the last session of my lectures. Thank you for that generous introduction, but I just want you to highlight a few things. I studied at University of Essex in the UK. I got a basic electronic systems engineering degree. From that point, when I went into the university, I wanted to go into satellite communication. I knew I wanted to do telecommunication as a specialist subject. And the chosen area of my studies at that point in 1997 or 1994 was satellite communication, because fiber optics was in a very infant age at that time. Sri Lanka wasn't part of it, and the whole world wasn't a big, part of this whole modern phenomenon. And even internet, when I were even in a UK university, the internet was only available in a computer lab. It wasn't available on your phone. It wasn't a readily available thing that you see today. So in 30 years, our life, um, the telecommunication world has taken a giant leap and made huge progress. I'm pretty sure by when I was in university, maybe some of you were not even born, and even if you were born, you were very, very little. So when the first time we were using internet, we used to do this thing called a dial-up internet, where you connect a little modem to your phone line, and it makes a beeping sound and turns on for about, it takes about 5 minutes to switch on, and then you are connected to the internet at a rate of 14 kilobits per second. And that by the time every year that kind of double, and we ended up around 56 kilobits per second by the time we got to 1997. So we did not have this fancy WhatsApp and Facebook time and FaceTime, and all these chat methods were not available. I can remember when I started my PhD in 1997, that was when the first chat system, which was called into Skype. There was no video conferencing facility. You can first, it was only a chat window, and after a couple of years, it turned into an audio window, and then into the video window that we see today. But that process took some time. So my work during my PhD was to go from 2.5 gigabit line systems into 40 gigabit line systems. Company, a few of us in the university, and I joined that company. And from that company, obviously we moved jobs and so on. Now I have been in industry unbroken for 21 years. And in that time, I have worked for some of these companies, Xterra, Ultima, Infinera. I think Ultima is no longer in fiber optics, but Xterra and Infinera are. And many other people who supply cables. So there are two parties in telecommunication industry. One of them are the people who buy the telecommunication equipment and provide you the services like your internet, which we call the ISPs, the internet service providers. And then there's the other set of people who actually build the equipment. You know, the router that hangs on your wall, the stuff that is in the cable landing stations or the exchanges, the people who manufacture the equipment. So I have worked for both sides. I work for service providers. I also work for the people who manufacture equipment, to test their equipment and see how they're going to perform over the years. So I was kind of getting a lot of consultancy work. So by 2018, I started my own firm. So now there's 2 people in my firm, and we turn over about 250,000 US dollars a year at the moment. And I started lecturing as well in 2017. I joined SLTC when they started. So I was their head of telecommunication until I left them. I wanted to concentrate more on my consultancy work. So I kind of also wanted to give the knowledge that I get from my experience overseas to students. So that's why I continue to do visiting lecturing at KDU. Now, what we are in the process of setting up a kind of research center for optical communication as well as light, open beam communication in using light or Li-Fi. Recently, between KDU, Sri Jawadanapura University and Moratuwa University, we were awarded a 50 million rupee grant from Asian Development Bank to do research into Li-Fi. I'm also working on a MOU between Moratuwa, Jawadanapura and us to create a super lab where all the students from these three universities can work in fiber optical communication. Now, when I was a student, we only visited the research labs. But as a person who is in industry now, I want you to give you some hands-on experience through your lecture series. Satellites were no longer used for telecommunication, and we'll talk about that later in this today's lecture. What happened and why the change. And at the same time, I kind of made a liking to one of the lecturers who was like delivering us the optical communication modules. So he offered me to work with him as a research student, and that changed my life. That changed my path from going into satellite-based communication into fiber optic-based communication. Now, because of that, the life, the opportunities that I have had in life and the paths that I have taken, the choices that I have made have taken me here. And it's an enormously rewarding job. One of the main reasons is I do like to travel. And as Pramod mentioned, that I have been to more than 50 countries. I do about 100,000 air miles a year. So I just on Monday I arrived from Kenya. So the view from my hotel, you can see what the view from my hotel is. And next week I'm off to Rio de Janeiro. So every week or every couple of weeks I get to travel to somewhere. And the beauty of submarine cables is wherever I go, I end up on a beach because submarine cables have to land on some beach. So I have also taken up snorkeling and exploring sea life because of these opportunities. So if any of you want to take down this path, there are not many engineers. I am finding it very difficult to recruit people with the right caliber for my own company. There's a huge set of vacancies out there, but it requires you to do hard things. Optical communications isn't easy. It requires you to have a good knowledge of physics and apply yourself into very hard tasks, mathematics, and even practical sense of things. So if you want to take down that path, and also you need to be willing to travel because none of my friends are never in one place at the time, anytime. So if you can afford these to take these, you should be able to make the journey. Okay, so I want to give you a quick one video session to recap where we are in the history of telecommunication.
Long before telecommunications was even a word, humanity was obsessed with its central concept, long-distance communication.
So just give me a second, I forgot to do something when I was sharing the screen.
Long before telecommunications was even a word, humanity was obsessed with its central concept, long-distance communication. Some 40,000 years ago, the earliest methods of relaying messages consisted of smoke signals. Homer wrote about the early Greeks' use of fire in the Iliad, and drumming, very loud drumming. This was used in Africa and Asia. Although primitive, these approaches were inventive at the time, relying on coded language. Certainly, there were other clever approaches through the centuries. The Greeks' carrier pigeons, the use of ravens in medieval times. But the real breakthrough came in 1451 with the advent of mass communication. Johann Gutenberg, a German goldsmith, invented the printing press. It replaced monks and scribes duplicating documents painstakingly by hand. The technology introduced concepts that we associate with the internet today: a one-to-many mode of communication, widespread access to knowledge, mobile information. The history of telecommunications is a story of evolution, and often, as in other industries, progress was incremental, inventions built on earlier ideas. In the 1790s, for instance, French engineer Claude Chappe built the first telegraphy system. For the 136 miles between Lille and Paris, stone towers were constructed as far apart as 20 miles and used to relay flag-based messages. Electricity changed everything. 50 years after Chappe, Samuel Morse and his colleagues created the telegraph. It relayed electrical impulses, Morse code, the descendant of those early smoke signals and drums, over wires. Soon, those wires extended across the country and even under the ocean. Instant long-distance communication was finally a reality. The telephone, invented in 1876, became a household device in the 1940s. It made telecommunications personal. Alexander Graham Bell's invention transmitted the human voice, in the early days, multiple voices, over shared party lines. The journey to modern telecommunications is punctuated not only with major milestones, but also with ideas that were ahead of their time. For instance, Bell's wireless telephone call in 1880. That breakthrough didn't catch on right away, but it eventually led to today's fiber optics. If the first 40,000 years were a methodical climb, the last 30 years have been a sprint. From the internet to smartphones to wearables, from email to texting to video chat. We all know this most recent chapter. We've lived it. What we may not have noticed, though, is how telecommunications has shifted yet again, from communication between humans to communication between machines. We live in a world where internet-connected devices are constantly talking to each other. More often than not, they're talking about us.
Okay, so this is a very brief history of our telecommunications. Just 1 second. Yeah, so this is a very brief history of telecommunications. So as human beings, I think when we were in small classes in school, we always learned that the 3 basic needs of human beings is food, shelter, and I think it's travel, right? So now, actually, one of the main basic needs of human beings is communication. And ever since people have been able to travel and discover new planets, we have been wanting to communicate with each other in faster and faster rates. So because of that, there has been a big need for building cables or coming up with techniques that we can talk to each other quite quickly. Now, in that journey, some of these people were mentioned in this video. There are 4 main people that I think changed the world of telecommunication. And first person here is Johannes Gutenberg. He's the person who created the printing press. So enabling the creation of multiple documents at the same time. So mass information collection and spreading was enabled by people like Johannes Gutenberg. Then you have this man, I think, who actually is probably as important, and perhaps for me in telecommunication more important than Isaac Newton, is Microfaraday. Because him inventing electricity was one of the main shifts that sped up telecommunication in the 19th century. because if any of you have seen Count of Monte Cristo, the older version, there is a scene where they relay a signal about the stock market from one end of the country to the other end by changing the flag signals. That is called the flag-based flag telegraph system. And he changed that into an electrical telegraph system by the end of the 19th century. And Alexander Graham Bell, he took that and converted it into a device that we can communicate with people over a long distance. Now, the last person here is Samuel Morse. Now, during your lecture series over the 4 years of your studies as a telecommunication engineer, you will learn about a subject called information theory. Now, one of the most important thing about transmitting data is that data is going to convey a message. And our objective should also be to make that communication very efficient. That means with a little number of bits, binary ones and zeros, we should be able to deliver the maximum amount of information. Right? Now, this is called entropy. So Samuel Morse created or put the first steps in defining an entropy. Now, you will start thinking what this lecturer talking about. Now, if you look at the Morse code uses a single dot for the most used letter in the English language. For E, he uses a dot. And for the least used word, he uses several dots and dashes. So depending on the frequency of the letter that is used, he uses the shortest code possible. And that makes the information transmission process very efficient. And that is called entropy. So these few people actually changed the world of telecommunication forever. And that brought it to the place that we are in today. So that is the end of my history lesson for the general telecommunication. Does anybody have any questions? You can open your mic and ask me. If not, I can go into the basics of fiber optic communication. Can we have optical communication? Let me check who owns underwater cables, what happened underwater cable breaks. Let me quickly go through the quick questions you have. How thick are underwater cables? I'll answer that later on this. Why don't companies? So some of these questions you have. I will answer some of them. So most of these questions will be answered by the end of this lecture or the next lecture, except the one about the telecommunication notes. Most of these notes are still available on the links that are shared in the lectures. So I haven't removed them. If not, I will have to talk to Dr. Shanika and come up with a solution.
Excuse me, sir.
Yes.
So we'll be having a separate Q&A session.
That's
today.
okay. That's fine. That's okay. I just checked through the stuff that you have sent. Okay, no problem. All right. Okay. So back to the basics. So how does a communication link work? So before we understand how fiber optics work, how does your general telecommunication link work? Most of us, we have instruments that generate data. Some of them could be computers, video recorders, telephones. Telephones convert voice into digital signals. Video recorders convert images or into video digital signals. And computers actually convert digital signals into digital signals. So we put all of them, we call them as message sources. And on the other end, we have to take that data and either put it on a loudspeaker if it's music, put it on a TV if it's video, and maybe on a phone or a phone for a voice. So we have to convert them and enable the other person to hear or listen or watch those information that you have transmitted. Now, as human beings, we don't create any digital data. I'm not sitting here talking to you 101111011111. Right? I'm creating a voice. I'm creating a sound, which is an analog signal. The microphone on my computer picks it up, converts it into a digital signal. And on the other side, the computer or any device that you're using converts it back from digital to analog, and then broadcasts it through the speakers of the device that you're holding. So that is called the message sync. So in between, we have to convert from analog to digital. So we have to have some kind of A to D converter. And that digital signal is modulated. Now I'll get to that modulation part. And then it is transmitted over a coaxial cable or radio waves. And on the other side, it is demodulated again. And then we detect and we convert it back to analog, and then we listen to the signal. So this is the process of a telecommunication link. Now, when we send a signal, if I were to shout from my house so that you guys can hear in your own houses, that is not going to work. My voice is not going to carry that far to your house. But how is this? How do you get TV signals? How does somebody sitting in a Rupwahini station talk to you in your own house? Why can't he climb the tower at the top of the Kotelawala mountain and shout at the top of his voice? Maybe you all can hear. Ultimately, his voice is what you hear, right? Our human voice and most of the signals that we perceive, the video and the images, they are all fairly low frequency signals. My voice goes from about 0 kilohertz to about 4 kilohertz. The images, the TV images, they go only about 5 megahertz. So they are not strong enough to go through the air. In order to something to travel through air or a cable, it needs to have high energy. In order to generate high energy, you need a higher frequency of data. So what we do in a modulator is we take the signal that I generate and I mix it with a sine wave or a cosine wave at a higher frequency. When you mix them, I can transfer the high energy of the high frequency signal into the information that I'm giving, and then I can send it over airwaves to reach your TV or the radio antenna. And that's how any telecommunication network works. So similarly, on the other side, obviously, you will not be able to hear a high frequency signal. Your ears can only hear up to 44 kilohertz. So then you need to somehow other remove that high frequency signal that we added and take back the information that was sent in. Now, this is like you are writing a letter. Right? You are writing a letter to you. I know you nowadays you guys don't write letters, but if you were to write a letter to somebody, you put it in an envelope. I mean, you don't take the letter and put the stamp on the letter and send it, right? You put it in an envelope. So envelope is like this high frequency signal. And you put a stamp and you put the address, nothing else on the envelope. And the envelope goes to the other end. The person cannot read the letter without removing the envelope. So this is what happens even in telecommunication. We put it in an envelope, we call it modulation. And that signal is then transmitted, and the digital signal is then converted and given back to us on the other side. Now, if you are transmitting this over a cable like your telephone, you can only get between from about 100 kilohertz to about 5 gigahertz. Even if it's a satellite based link, you can only go from 0 to about 5 gigahertz. Now, The other thing you can do is you can convert, rather than sending electrical pulses down a line or converting electrical pulses into a radio frequency, you can convert electrical pulses into light pulses. So in order to do that, we need a light source, and you need to switch on and off the light source according to the digital signals that come. And on the other side, we need to detect the light signals, light pulses that come in, and convert that back to electrical pulses, so that then you can do the A to D conversion and hear the information in your speaker, the computer, whatsoever. So now in fiber optics, we use the frequency band between 191 terahertz to 195 terahertz. Now there's a big shift. If you look at radio waves, we were using 100 kilohertz to 5 megahertz, 5 gigahertz. In here, we are using a far higher frequency than what we were using in radio waves. And in between, you have an optical signal. So you get this conversion and you receive the signal. So we need to have something that converts an electrical signal into an optical signal. And on the other side, we need to have something that converts an optical signal back to electrical signal. So for this, we can nowadays, we use lasers. Now in my fiber optic communication lectures, there we will go very much detailed into how these optical modulators work, how the lasers work, and why do we need a laser. So we go very much into detail. I'm not going to go into that detail in here. And even on the other side, the recovery, what different devices we use. So there is a whole set of things that you will learn in fiber optic communication. But the basic concept is that we convert an electrical signal into an optical set of pulses and we send it through. Now, the best way of converting optical signals to an electrical signals into an optical signal is by switching on and off a laser. And you guys can think of, you want to send a signal to your next door neighbor, right? You guys have agreed on Morse code. So what you can do is you can switch on and off the light that is facing your neighbor with the switch, depending on the Morse code. And if he is looking at the flashing of the light, then he can figure out the code that you are sending and get the message. Now, if you guys fall in love with the girl next door and your parents are against this, perhaps this is a good way of communicating without them knowing. So how do we convert from electrical to optical and optical to electrical? So this is one of the basic things that we need in the communication systems. So here what we do is we have this laser diode, and in a laser diode, so you have, I will not explain how a laser diode works here, but it's in my lectures. In a laser diode generates a single frequency, a very tiny frequency of the light. They're all going in the same direction. They go all in the same polarization, and it will reach, and they're all parallel to each other. So it is easy for you to couple in light from a laser into a optical fiber. Now let me explain this. You guys have normal lights at home, right? Now if you in the night, if you take a torch, you guys have seen the old torches with the incandescent bulb. අර පොඩි bulb එකක් දාලා ඔයගොල්ලෝ torch අරගෙන යනවනේ රැට battery අර D type battery දාලා ඉස්සර තිබුණේ ඔයගොල්ලන්ගේ CL පාවිච්චි කරපු torch. එකක් අරගෙන පාරේ ගියොත් how far can you see? If you take a torch that used by one of your grandfathers with an incandescent light, can you see a long distance? How bright is that light? Now, modern day, we use LED lights, right? If you were to take one of the modern day torches, or even the light from your mobile phone, isn't that more brighter than the torch that your grandfather carried? Isn't that light go a longer way, further than anything else than your grandfather carried. Now, if you were to take the same thing, you see these laser pens the lecturers use in the class to point at the screen. If you take one of those laser pens at night and aim at a distance, don't you think that laser pen goes further than the LED light or your grandfather's torch? So this is why we use lasers. Now, even the lasers that you use in pointers, they are not as good as the lasers that are used in fiber optics. And so um, that's why we use laser diodes in fiber optics. Now, the other method, okay, so now we established that we use laser diodes. Now, how do we switch on and off the laser diode in varying with the data? So one of the ways that you can do is we can connect the laser diode, the power on, power off button to the electrical pulses that come in. So then when the electrical pulses goes 1, the laser diode switches on. When it goes 0, laser diode switches off. So from that, you can create a stream of ones and zeros. But unfortunately, this process is very slow. Again, I go back to an example that you have in your own house. If you guys look at a fluorescent tube in your house, what happens when you switch on a fluorescent tube? As soon as you switch on the fluorescent tube, does it come on and give you light? Or does it sometimes go flicker a little bit, tries to switch on a couple of times, and then all of a sudden switch on? And then when you switch off this fluorescent light, does it go dark straight away, or can you see a little bit of light for another few seconds before it goes dark? And I think that is the case, right? Now, if you switch off any light, any LED, any laser in that way by switching an on and off the power source, it takes some time for it to start up and come to a stable light output. And when you switch it off, it also takes some time to completely switch off the light. Now, this process is called an oscillation. And because of the oscillation, you cannot switch on and off a laser or a light as fast as we want to. Now, the speed that we can do this by switching on and off the light is about 5 megahertz to about 10 megahertz. Now, today, the communication that I'm doing, the work that I am working at, the data rates that I'm transmitting under the sea today is between 500 gigahertz to 1 terahertz. So how can I go from 10 megahertz to that achieve that fast switching on and off rates? So for that, we use a technique called external modulation. Now there's a long story about how this thing came, how people found out about external modulation. Now I'll explain it to you. All of you have been Vesak. Oh, have you guys all been to see Vesak lanterns at some point? May COVID වලට කලින් ඉස්සර මේ රටේ වෙසක් තිබුණාම තිබුණනේ වෙසක් කූඩු එහෙම. දැන් ඔය වෙසක් කූඩු තියෙනකොට, sorry if anybody doesn't like me switching between Sinhala and English, let me know. But I like to explain this story in Sinhala because that's how my dad used to explain it to me. The Miss වෙසක් කාලෙට මොහිදින් බෙග් සින්දු කියනවනේ ඔය පාර දිගේ ස්පීකර් එල්ලලා හාමුදුරුවෝ කොමේ වෙසක් එක ඕගනයිස් කරන මිනිස්සු හැම ලයිට් කණුවෙම හයි කරනවා මේ ස්පීකර් ෆෝන් එක නේද? So when you are walking towards passing these speaker phones, because there are two speaker phones equally distance, you could create constructive and destructive interference between two speaker phones. එක speaker phone එකකින් එන එක අනිත් speaker phone එකකින් එන signal එකත් එක්ක එක උඩ ගියාම you will have constructed interference. And if they are out of phase, one of them is 180 degrees out of phase, but it's the same signal, they cancel each other. So if you are walking from one end towards this Vesak Kudua, and if you are passing several of these loudspeakers on the way, ඉතින් මොහිදින් බෙග් ඔන්න ඔබේ රාගී මන කැළඹේදෝ කියලා කියනවනේ. ඉතින් ඔයා දැන් ඇවිදගෙන යනකොට ඔයාට එන ඔබේ රාගී මන, and then you will hear nothing. Again you will hear at the top of the voice. So what happens is you create constructive and destructive interference, because two signal sources are sending the same data, but because when you're walking, your two ears can pick it up at 180-degree phase shift or a 0-degree phase shift. Now, they use the same principle to create a faster switching. So this thing called the Mach Zehnder interferometer, what they do is they use the same principle. They use one laser source which is permanently switched on, and they split the signal into two parts, and in one part they apply electrical signal. Here is where you add your data. Your ones and zeros are added to this path here. Now there is a property of light. If you apply an electrical field across light, you can speed up the light or slow down the light. So in an optical fiber, if you apply electrical field, in a certain electrical field, you can speed up the light. In a certain electrical field, you can slow down the light. So now if I apply 1010 pattern here, and if this light, by applying that, if I can create a phase difference of 180 degrees and 0 degrees, I can create a pulse through constructive and destructive interference. And we found that doing this method, I can create very fast signals, very fast optical pulses, rather than actually switching on and off the laser. So this method is called an external modulation technique. So today all optical communication systems use external modulation systems. So on the other side, how do we recover the signal? Now we use a diode, and now all of you will start thinking, sir, කොහොමද මේ diode එක පාවිච්චි කරන්නේ? So in a diode, you have a p-type region, holes වලින් සම්ප්‍රයුක්ත වෙච්ච p-type region, then electron වලින් සම්ප්‍රයුක්ත වෙච්ච n-type region. So when you bring these two together, some of the electrons will jump and make families with the holes, and they create this region called intrinsic region. So when light falls on the intrinsic region, these bonds between here, they break. And this is like a relationship. So we have male students here, female students on this side. When you put them in one class, some of them will become couples. And when they become couples, they become together. They don't hang around with the boys. The girls don't hang around with the girls. So they hang around with each other. So they all go into this little lover's corner, and we call it the intrinsic region in a laser. Now when light, even though these couples are sitting in the intrinsic region, if the boy sees another nice girl, or if the girl sees another nice boy going past, sometimes that could break the bond. So intrinsic regions are more susceptible to when laser light falls on them. Light is also a source of energy. It energizes these bonds. Once you put energy into a bond, those bonds can break. So it could create more holes onto one side, more electrons onto the other side. And because of that, a small current can flow through the region. So we, in order to detect light, we create specialist PN junction diodes, where we have a big region where there is an intrinsic region, where there's lots of bonds between electrons and holes in this region. And if I create a bigger area, it's easier for it to capture more light. If more light is captured, then these bonds that are inside this intrinsic region break. It releases holes and electrons will flow through an electrical circuit and convert the light into electricity. This is what happens in a photodiode or a LDR, all these circuits. This is the principle. So by doing that, we can take a light that is coming into a photodiode, and that photodiode will generate an electrical signal. An electrical signal, we need to extract the clock frequency and convert it back to the original data. So this is the simple process that how you transmit. The other side, how you convert optical pulses back to electrical. In modern telecommunications, and I will get to this again in another 2 weeks' time, we no longer use amplitude shifting. Amplitude shifting means if you have a series of ones and zeros of electrical data, we create similar optical pulses and no pulses in the optical data. So instead of doing that, we can create phase signals. So we can create phase changes, and we can recover that. So this is the technique that is used in modern communication systems. I will get to that later on next week. Okay. So now I told you how we convert electrical data into optical data. I also showed you how we convert optical data back to electrical data. Now, what are the light? What kind of light do we use? What kind of frequencies or wavelengths do we use for this process? Now, the light that you see, the light that comes from your LED light or the light that your eyes can perceive is from about 300 nanometers to about 700 or 800 nanometers. This is we call the visible light spectrum. And here, the ultraviolet side is not very good for your eyes, so you should not look at them. You should, but the infrared region is something your eyes can take. But for optical transmission, we don't actually use any of those wavelengths. We use frequencies between 800 nanometers to about 1,600 nanometers or 1,700 nanometers. Now, the problem with this type of wavelengths is you will not be able to see it with the naked eye. So, in effect, working with fiber optic cables is fairly dangerous. The reason being, if there's a fiber cable break, or if you look into a laser diode directly in your eye, you will not be able to see any light. But the light is there and it can cause severe damage to your eyes. It can cause severe damage to your skin. So light at a high power is a very dangerous tool. So therefore, when you are working in fiber optics labs and any fiber optic equipment, please do not ever disconnect a cable, disconnect a connector and look into it, because your eyes will not be able to pick up the light that is coming out. And high power light, anything above 10 milliwatts, if you look at them for a few seconds, you will damage your eyes. Now, some of the lasers that I work with are not just 10 milliwatts. There are lasers that I'll be working next week with. They're in the range of 2 to 3 watts. Now, if you have a laser diode with 2 to 3 watts, I can sit near the gate of KDU, the front gate, and write my name on the wall in the engineering building. They are that powerful. So you have to be very careful when you come to my lab, and that's one of the important aspects. But as I said, the human eye can only perceive this band. So optical communication, although uses this part, but mainly for fiber communication, we use from 800 nanometers to about 1700 nanometers. So why are we using this kind of different frequencies? People, so this optical fiber is made out of 2 pieces of glass, right? There is a cladding and there's a core. And When they send light through the frequency to find what is the phase or what is the frequency that has the lowest attenuation when it goes through. Then when you send any signal through any medium, there is attenuation. Then that means that naturally the signal energy will waste away. Now, like so, if you were to use radio waves, the radio waves decay at the square of the distance. Now, when you learn telecommunications, you will learn if you have an antenna at a station A, person who's L kilometers away, the signal degrades by the square of the distance. But in cables, signals degrade proportional to the length of the cable. So that means sending data through cables creates less loss. But in radio coaxial cables, the loss of the data increases with frequency. Then I will explain this to you in a different way. When you go to the engineering lab next week, take a signal generator and take an oscilloscope. You connect a coaxial cable between the signal generator and the oscilloscope, maintain a 2 volt peak-to-peak signal, and start increasing the frequency of the signal. Tell me what happens to the signal that you see in the oscilloscope. I am pretty sure the signal will stay, you send 2 volts peak to peak. For us up to a certain frequency, you will see 2 volts peak to peak on the oscilloscope. But after a certain frequency point, the amplitude you see in the oscilloscope will start to go down. And that is not because there is a problem with the oscilloscope, but the cable, the coaxial cable, will start to attenuate that signal, take the energy away. So at certain frequencies, that coaxial cables will have this problem. With fiber optic cables, it doesn't depend on the frequency of the signal, but it depends on the wavelength or the wavelength of the light that travels through it. So people in around 1980, they found that 1.55 nanometers or 1.55 micrometers or 1,550 nanometers is the lowest point of attenuation in fiber optics. So modern cable systems use this advantage of this particular point, and all our transmission is done on undersea cables at that particular frequency. So we transmit from about 1.53 micrometers to about 1.56 micrometers. So very small range because the attenuation is the lowest at that point. So
I find this a fascinating object. It's a fiber optic cable for a stereo. If I shine this laser pointer down the cable, it guides the light out the other end. These cables are used to connect our world today and are capable of transmitting information across countries and oceans. But first, let me show you how it works. On this plug, when I turn out the lights. That's wonderful. The light follows the liquid flow all the way to the bucket. Amazing. It does this because of total internal reflection. As the light enters the stream, it is reflected as soon as it hits the interface between air and liquid. You can see here the first reflection, and then the second, and the third. This occurs because there's a difference between the index of refraction of the guide material, here propylene glycol, and the outside, air in this case. Recall that any time light strikes a surface, it can either be absorbed by the material, reflected from it, or pass into and through it. The latter we call refraction. It's easier to see from a top view. Reflection and refraction can happen at the same time, but if a light ray hits the surface at an angle greater than the critical angle, it will be completely reflected and not refracted. For this propylene glycol and air system, as long as a beam hits the surface at an angle greater than 44.35 degrees, measured from the normal, it will propagate down the stream via total internal reflection. To create this same effect in an optical fiber, engineers create a core of glass, usually pure silicon dioxide, and an outside layer called cladding, which they also typically make from silicon dioxide, but with bits of boron or germanium to decrease its index of refraction. A 1% difference is enough to make a fiber optic cable. Called TAT8, it extended from Tuckerton, New Jersey, following the ocean floor over 3,500 miles until branching out to Whitmuth, England, and Ponmarsh, France. Engineers designed the cable carefully to survive on the ocean floor. At its center lies the core. Less than 1/10 of an inch in diameter, it contains 6 optical fibers wrapped around a central steel wire. They embedded this in an elastomer to cushion the fibers, surrounded it with steel strands, and then sealed it inside a copper cylinder to protect it from water. The final cable was less than 1 inch in diameter, yet it could handle some 40 thunderbolts, can travel nearly 4,000 miles across the ocean. It doesn't without some help because the light will escape from the sides of the fibers. Look back at our propylene stream. Here's how the light attenuates as it travels. You can see here a narrow beam in the bucket that broadens a bit when it enters the stream, and then after the first bounce, the beam leaves even broader than it entered. That's because the interface with the air is uneven, and the rays that make up the beam strike at slightly different angles. When that beam makes its second reflection, those individual rays diverge even more, until by the time it reaches the third bounce, many of the rays are no longer at the critical angle and can exit from the sides of the stream. Here it happens in a few inches, but in a cable like TAT8, the signal travels a stunning 50 kilometers before it needs to be amplified. Absolutely amazing.
Okay, so that was just a quick, sorry. That was a quick introduction to how fiber optic cables are made. So fiber optic cables have a core which is slightly high refractive index and a cladding which is outside that, which is slightly lower refractive index. And a fiber optic cable is the size of a hair. The internal core is about 10 microns. The outside core cladding can be up to about 100 micrometers. So you can imagine a single optical cable is only 100 micrometers in diameter. So smaller than your hair. So the real pioneers who actually started the ball rolling in terms of fiber optic cables was these guys called Jacques Babinet and Daniel Collodon, who saw that light can be bent through water, and so that in glass rods as well. So then this guy here is John Tyndall. He demonstrated the first principle of total internal reflection. Today we use total internal reflection as the main source of guiding energy through optical fibers. Now you can see these discoveries were made in 1854. So why did it take so long as 1980s for fiber optics to become a everyday occurrence? Why didn't we go to fiber optics in 1980s? And by 1920s, people were actually using endoscopes and so on to look at your stomach. For medical purposes, we were using fiber optic cables as early as 1920s and 1950s. So why didn't we take up telecommunication, didn't take up fiber optics? The reason being, we did not have a suitable light source to guide light this further distance. We did not understand how the different frequencies go through optical cables. And until 1970s, we could not get down, reduce the attenuation of light through an optical fiber. And the actual people who made this possible, first person I to give my hats off to is this guy called Charles Hart Towns. He was the first person who came up with the idea of the laser. It's stimulated emission of light through amplification. Um, no, light amplification through stimulated radiation, emission of radiation. And he was the first person who created an laser. Now you can see one of the lasers he created in the picture on the right hand side. Obviously, you cannot use that in telecommunications because this is a bench device. It is like the first computers they built during the Second World War. One computer was the size of one room. So one laser was size of one lab. So it took some time from 1951 in order to miniaturize and create an optical laser in a small circuit that can be used in fiber optics. So Robert Hall, you might have heard the effect called the Hall effect. He's the person who came up with it. He was the first person who came up with a semiconductor laser diode. So that means a laser diode is implemented on a semiconductor, and that is capable of transmitting over the distance. Now, from that point, a French physicist, Fabry Perot, he created a laser that can be used in fiber optic transmission. By 1989, we managed to get a very narrow laser, which we call the distributed feedback laser, that was suitable to carry data over a long distance. From that point, more advances have happened, and today we are using these things called ITLA or cavity lasers, which has very narrow line widths and can travel very, very far, long distances for our communication. So we needed a very strong optical light source for our transmission. Now, the next chapter came out because of these people. This is the two top pictures is Charles Keogh and George Hockham. They were the first people in 1966 who introduced fiber optic as a telecommunication method. So from 1870, it took almost 100 years to realize light transmission into telecommunication. In the first time, we managed to send a telephone call over a cable, was not undersea or over a land cable, was in 1977. Now by 1980s, world has already started. Already land cables were laid, and these were mostly regeneration. Regeneration means we send an electrical signal. When the strength goes down, we have an electrical data signal. We convert it into a set of optical pulses. We send it down a certain distances. When the signal becomes very weak, we convert it back to electricity, and we use electrical amplifiers to amplify the signal. And then we convert back to optical, and we keep doing this at every side, which we call regeneration. We have every amplification side. Amplification was done electrically. So in 1986, Emmanuel de Sevilla, which is the right person in the right bottom right, Randy Giles, which is the person in the far left, far right, and the person in the middle is Sir David Payne. They all came up with the idea of creating an optical amplifier so that light passing through that amplifier can get amplified. So you didn't have to convert light back to electricity to amplify the light. So this was called an erbium doped amplifier. It was developed in 1986. All these people have received, been knighted or received the highest accolades for this. And that meant that discovery in 1986 changed the world of fiber optics, so that we did not have to convert a signal into electricity and back to optical as it goes along the fiber. The first fiber optic cable was laid in 1988. So again, it took almost 10 years or 20 years from using it in land to use it under the sea for the first fiber optic cable. So that cost $335 million at that time. It was installed in 1988 and it was retired in 2002. Now, this was a regenerative system. That means under the sea, there are amplifiers that convert from optical to electrical. Electrical amplifiers amplify the signal and they convert it back to optical. So TAT8 was such a system. The first optically amplified signals where we did not have any electrical conversion in under the sea, that happened in 1996. The first one was TAT12, TAT13. You can see now they discovered the amplifier in 1986. It took almost 10 years from the research to go into industry, to go in under the sea. And that cable was retired in 2008. So now this brings to the last part of today's lecture. I'm just going to give a quick history about all the submarine cables. Now, putting a cable is one challenge. Putting a cable under the sea is a much bigger challenge. If I were to run an optical cable from Colombo to Jaffna, it's not that much hard because let's say I go 50 kilometers, I need to amplify. In order to amplify, I need some electrical power to use for my amplifiers. So maybe I can stop in Kurunagala and connect to a plug and create electricity, amplify the signal. Next stop Dambulla, next stop Anuradhapura, next stop Vaunia. Like that, you can every 50 kilometers or so, you can have an optical amplifier plugged into the main grid to amplify my signal. But when you're putting something down under the sea, you don't have that luxury. You cannot plug on to some kind of a plug socket under the sea to amplify my signal. So the distance between UK and USA is about 6,500 kilometers. The distance from Japan to USA in the Pacific is close to 9,000 kilometers. So how can you travel 9,000 kilometers without having an amplification process? So these made doing doing cables under the sea far bigger challenge, and even to this day that remains an enigma in our field. There are more engineers who work on terrestrial or networks that are over the ground. There are very little number of engineers who actually work on cables that are under the sea, because that's a highly skilled area. So go to my last part of today. One of the questions you asked me earlier in the questions, sir, why are we bothering with these fiber optic cables? I mean, we have to convert to optical, we need to have amplifiers, and now I'm telling you that we cannot find amplifiers under the sea. So why bother? Why go through this whole hassle? Why can't we just go send up our signals to a satellite and get it back? So the biggest question, I'm connecting Tokyo to Los Angeles. I said it's about 9,000 kilometers. So if I lay a cable under the sea, the distance I have to travel is 9,000 kilometers. If I put a satellite up there, if anybody knows about geostationary satellites are about 36,000 kilometers above the sea level. So if I send a signal from Japan to a satellite, that takes 36,000 kilometers, another 36,000 kilometers to come back down. So it travels 72,000 kilometers, which is almost 8 times longer than the distance between Tokyo and Los Angeles. So what happens to a signal that travels further? Any of you who live next to KDU can come to KDU very fast. Somebody who's traveling from Gala or Kandy every day will take you a long time. So this is the same problem. The amount of time it takes for my data to start from Tokyo to Los Angeles through a cable is much shorter than the time it takes for my message to arrive through a satellite link. Now in today's world, every second matters, every microsecond matters, every nanosecond matters, because stock market traders want to get an advantage over in any way, right? So if I can create another optical cable between Tokyo and Los Angeles, which is 8,500 kilometers, all the people who are running the stock market will buy capacity because they will get a small advantage, small few microsecond advantages of their competitors. The time it takes for a message to go from the transmitter to the receiver is called latency. And higher the latency, it's not very good. So that's one of the problems we face in using satellite communication. Secondly, obviously, satellite communications are very expensive. Not everybody can put the satellites up there. To maintain a satellite, it costs a lot of money. And also today we have a lot of satellite debris because people have been putting up satellites. Satellite we have so much garbage in our stratosphere. So we need to start cleaning up this space garbage as well. And then the amount of data, the bandwidth. Think again, I want to take you to an example. Oyala Komala FM radio, right? Now, your FM radio in your car, if you start tuning it from one end to the other end, it starts at 88 megahertz and goes up to 108 megahertz. Now, if you start turning your tuning range, every 150 kilohertz, you will find a new station. 150 to 300 kilohertz and 95 කියන්නේ net FM 95.3 කියන්නේ මොකද යාත්‍රා FM දෙක හැම kilohertz 300ටම you have another station, so that the gap, the FM band, the amount of frequencies you can have is called the bandwidth. From 108 megahertz down to 88 megahertz, that 20 megahertz is called the bandwidth. So that's how much data, how many channels you can put in there. Now in a satellite, I have only 36 megahertz bandwidth. අපි 4 gigahertz වලින් signal එක යවුවට the actual data අර envelope එකේ දාන්න පුළුවන් ලියුම් ප්‍රමාණය බොහොම චුට්ටයි satellite එකට යන. Cable, fiber optic cable provides you a 4 terahertz bandwidth. So if you compare megahertz with terahertz, terahertz is 1 million times bigger than megahertz. So I'm getting a huge amount of data that I can transmit through a single optical fiber compared to a satellite. And then obviously I talked to you about the latency. It takes 24 milliseconds for a signal to go this route compared to 45 microseconds for the signal to go that route. Now, in the when I first started studying in England, most of the calls in Sri Lanka were sent through satellite phones. And so when you speak to somebody in a foreign country, when you speak, the other side goes silent. And it takes some seconds for the person to get my message and for them to respond. Nowadays, you don't have that delay. You don't have that blackout. You don't feel that the other person is not next to you. So the main reason for that is the reduction of latency in cables. Now, most of you, as you said, talked to you about, all of you are hopefully going into telecommunications, and most of you are looking at jobs in mobile market. And I can understand that because mobile looks very fashionable. There's many companies in Sri Lanka that supports mobile communication. But in reality, the way we communicate today is different. In 1980s, we had the data in our own computer. Once you connect to the internet, somebody wants some data from your computer, they can only access that data when you are switched on. Now, when I was, mid-1990s, there was a music sharing site called Napster. So lots of people in Sri Lanka, they converted Sinhala songs and we were sharing songs but you can only download some from somebody when they are online. Now today, if you want to download something from Facebook, or if you want to download this lecture that I'm giving tomorrow, you want to listen again, you don't have to wait for my computer to be switched on. You don't need the IEEE website to be switched on, because this data is stored in a data center. This information goes into a data center, into a big hard disk, which is switched on 24/7. So anybody in the world who wants to get that data at any time, they can download that data. Now, what I'm trying to say is, apart from this cloud here, which is called the access layer, which is the radio frequencies, everything with these rainbow lines is a fiber optic cable. Everything that goes underneath the sea is a fiber optic cable. Even when you make a call from a mobile to another mobile, 90% of that call goes on a fiber optic cable. The only part that goes in a radio wave is from your mobile cell phone to the cell phone tower, and from the other recipient's cell phone to the cell phone tower. The cell phone towers and everything in between are connected with fiber optics. So fiber optics play a far bigger role, and probably the biggest component in any network is the fiber optics. Then, so I wish to close it here for today, and then we start looking at submarine cables, from copper submarine cables, in the next session. So I think there is a lot of information for you to take, and the next session is going to be very exciting, because this is where I'm going to give you all the secrets. How do we lay the cables under the sea? What happens when you break? And how do I provide electricity under the sea? Do I have to dive under the sea? Do I play it on the floor of the sea? How do I plan a cable? So all this information will be divulged to you on the next session. This was only a taster for today, to give you an introduction, to excite you, to read a little bit about this before you come to the next session. Go through my video between now and then. And then obviously, as I said, the third session will be looking at the future. What kind of job market will you have when you leave university, and so on. So if you have any more questions, you can put them on the chat. Let me see if I can answer some of them now. Or if you want to ask them directly, you can open up your screen and do so. I have no problem with that as well.
Thank you, Dr. Sumudu.
Welcome.
Seems like we've gotten quite a few questions from the audience. So let's move on to our Q&A session. Let me start by asking the first question. So the first question is, what is the frequency spectrum of the lasers used in fiber cables?
I think I have answered that. As I said, in fiber optic cables, you can use anything between 850 nanometers to about 1700 nanometers. But the real usable part is between 1.53 nanometers towards 1.57 nanometers. That is the part that we use in the undersea communication systems, because for one reason, that is the lowest part, or in any optical cable, that provides me with the lowest loss, lowest attenuation through the cable. Okay. I think some of these questions, like cable breaks and so on, I will answer them next week. I think they are naturally in my lecture notes. So I'll quickly go through and see if there's anything that wasn't addressed and should have been addressed. How much information can a cable carry? Again, I will talk to you about that next week with some examples. Why are many cables between some subcontinents, but no cables between Australia and South America, for instance? Now, obviously, telecommunications developed mainly between Europe and US, and that is the biggest human mass who are having money and who can afford to communicate, well, spend money. And most of the tech giants are based in these countries. Most of the data centers are based in these countries. So that's why most of the cables are between USA and Europe. But not saying that there's a significant amount of cables that are laid between Asia and Europe. And now with the Middle East being very rich, and also countries like Singapore and Hong Kong are being rich, those countries connect with Europe capacity. The modern cables, the newest cables, and in the Pacific Ocean. There's also a question, why are no cables between Australia? So what we do is, in order for us to get more data in a cable, we prefer to go between land sites. So there are cables from Australia to Hawaii, Hawaii to US, Australia to Hawaii, and Hawaii to Japan. So Australia is connected. New Zealand is connected very well. There are many cables that are being laid as we speak. And probably the least connected continent in the world is obviously Africa. It's mostly due to financial reasons. But the 5G technologies are driving more capacity on the cable. So now there is a new cable being built called Equianos. So huge amount of cables have been built. And again, like we have with the space debris, we have a problem with what do we do with all cables that are in the sea. Sometimes it is not worth removing them out of the sea, but then that we are creating pollution. So and we in the earth we are running out of resources as well. The special the metal that we need to create optical fiber cables, we are running out of them as well. So there is a requirement to remove the old cables, reuse them. So there is a lot of activity happening. I like to talk to them about them in the last session on my discussion series, when we look at the future of the industry. So there's a question about chromatic dispersion and similar issues. I want to really keep this to more generic stuff. I don't want to really go down into chromatic dispersion. I will explain some of these facts, but I don't really want to go into a full detailed fiber optic communication lecture here. But I will touch some of that in the next lecture. So anything else you guys want to ask? You think that might not be addressed next time? So there's a message from the Dean congratulating you all for organizing this. So thank you students for listening and the lecturers who have joined.
Yes, sorry for interruption. So it was a very informative lecture, Dr. Sumudu. Thank you very much for helping us using your free time. And it is great to listen to you. Very informative lecture. So thank you very much. And also thanks goes to the Comsoc organizers for this wonderful lecture. I am eager to see and listen to your next lecture too.
Thank you.
Thank you very much. Have a nice evening.
Thank you. Okay, thank you, students. I think we'll. I think the date, Manupa and Sachit, that we will not be able to meet it next week, right? I am traveling on that said date. So, is it possible for us to either bring it forward to Saturday or delay it to some other day?
So I think 23rd is the suggested date.
Okay. Okay, that's fine. 23rd is fine by me. Yeah.
So Saturday is also fine.
Okay, so 23rd is fine with me. Unfortunately, the 19th and the 20th I'm traveling. So if we can arrange another date for that, that would be fine.
Thank you, sir. And thank you for enlightening us with your knowledge. So we are almost at the end of today's event. So I kindly invite all of you to switch on your cameras to capture a moment of today's event. The photo will be taken after my countdown. So everyone please switch on your cameras. Okay. 3, 2, 1. Thank you, everyone.
Thank you. See you in the next one.
Before we wrap up, I invite Kevin Pereira, the Secretary of IEEE Communications Society of KDU, to propose the vote of thanks.
Thank you, Sajid. A very good evening to all of you. On behalf of the IEEE Communications Society of General Sir John Kotelawala Defense University, and on my behalf, I would like to extend my heartfelt gratitude to all of you present here today. My deepest gratitude goes out to the speaker this evening, Dr. Sumudu Edirisinghe, for joining us despite your busy schedules and for conducting this session thoroughly and giving us a head start on submarine cables. Moreover, my appreciation goes out to the Dean of Faculty of Engineering, Captain Retired S.U. Dampage, Professor T.L. Veeravardhana, Head of Departments, Advisors of IEEE KDU, Advisor of IEEE Comsoc KDU, Dr. Sanika Vijayasekara, for mentoring and guiding us throughout. My special appreciation goes out to the team behind the scenes, the Executive Committee, Board of Directors, and team members for their immense contribution as well. Last but not least, I thank all the participants who joined us today. I hope all of you got a deep insight on today's session. Do stay tuned for session 2, which will be commencing soon. Thank you and have a good night.
Thank you, Kevin. Let me take a moment of your time to kindly remind everyone here to follow us on our social media through the links provided in the chat. The links will be provided in the chat. So this brings us to the end of today's webinar session. I am Sachit Plienage signing off for today. Thank you and have a good night.